The last conference I went to, I introduced Pino and said it was my first visit to Italy for 12 years. I'm ashamed to say this is my first visit to Belgium since the category meeting in 1987. Anyway,
welcome back.
Welcome, thank you. Right. And it was a pleasure to see Francis Dresden's there yesterday. Okay, so this is a category theory conference, and everybody else has come here with their sophisticated categorical constructions. Well, I have a few. You can find them on my web page. This address is in my abstract. And well, that's what there is. But what I'm going to tell you, so other people's constructions, you won't be able to remember them without studying their papers. I hope that what I'm going to tell you this morning, you will be able to reconstruct, at least from reading my slides, because it's a very simple result. Unfortunately, people will misrepresent it, and they say that this has to be proved using ordinals. And so you could, if I say an example of this, if you look up in Wikipedia and will party bit form theorem, you'll find a misrepresentation, a willful misrepresentation of how it's proved. In fact, what I'm going to say to you is pretty much following up the message of a paper by Kuratowski 100 years ago. And for even those of you who don't read French, I'm sure you can see what the message of this paper was. That is the message that I'm going to continue in what I'm going to tell you. So, if you were going to prove something using ordinal recursion, you would use this theorem here that translates induction into recursion. And I'm not going to talk about the theorem, but the proof of it. So the proof is due to von Neumann, 1928. And the components of the proof are that we talk about initial segments, so this is subsets on which partial solutions are defined, a successor operation on partial solutions, and taking unions of them, and then the required total solution is the unique fixed point of the successor, which is the greatest initial segment and greatest attempt. And this is a very common form that you'll see in other forms of recursion, and the reason why I was forced to come back and reconsider it was because I was considering well-founded co-arduous recursion for them. So von Neumann's proof considered the union of all attempts, so he was working over a complete lattice, and there's a misattributed theorem about fixed points in complete lattices. You'll notice that the two dates coincide there. But in many algebraic situations we don't have complete lattices. It's difficult to form binary joins in many algebraic situations, and the answer to that was to consider joins of chains. Classically, the answer was to consider joins of chains. Constructively, we replace chains by directed subsets. And I needed to relax that for the generalisation of the work on well-founded co-arduous. So the order theoretic fixed point theorem that we're talking about is we've got a closed set with the least element of directed joins and an inflationary monotone Pino function then that has a least fixed point. And we're going to sharpen the results on this. So
are you touching the microphone with your left hand?
I'm trying to hold it the right distance away. It's not working. Let's try.
Put it on your back.
Yeah, I tried that, but it was too close.
It can't be worse than
Is that okay now?
Yes.
Okay. I prefer to project my voice anyway. Okay, so we're going to turn this into a sharper tool than just least fixed point. And of course it's not. Yes, okay, so there's a classical proof of what I'm doing. Once again, this is misattributed. It's called the Bell-Schmidt theorem. And actually the proof is in Zermelo's second proof of the honorary theorem. in 1908. And say, and 1908 is also the year that he introduced the Melo set theory in order to prove his theorem. Okay, so the constructive proof of this. So people did not find this, partly because we were brought up with this set theory and the idea that everything had to be done with ordinals, also just blindness. So those of us who did domain theory in the 1980s should have known this. So the inflationary monotone inflationary endo functions of any DCPO form a directed set simply by composition. Why didn't we notice that? Right, those of us who were doing domain theory, and therefore because it's directly complete, it has the top element. Proof, easy proof. Much easier, by the way, than the Markov-Witt theorem. Traditionally this would be turned into a fixed point theorem, but we've got this DCPO which has got, somewhere in the middle of it has got a fixed point, and there's also a lot of other rubbish that we need to get rid of first, either by the Markov-Witt method or by Dito Paterno's proof of it. We have to get rid of the rubbish first. So how can we do that? So the traditional way of doing that was to generate the subset from the least element and the successor and the directed joins, and that gets you down to what you want. But this uses second order logic. So we're doing a piece of recursion. We put a piece of recursion as an hors d'oeuvre from the main meal. We intended to do a recursive result. We're feeding in what I will demonstrate to you is unnecessary recursion before we actually start on it. So is there a better way of doing it? Yes, there's very simple ways of doing it. So the third one, those three do the same job. You don't need to take them all in. So I actually discovered the third one first. The first one could have been, anybody could have done this 100 years ago. We take the things which are less than all possible fixed points and just concentrate on those. And I'm going to call these things well-founded elements. Right? So notice, by the way, that this is an algebraic property. There's essentially no logic in this, it's just algebra. And I'm going to apply some simple algebraic ideas to develop that. And any of these things give this intermediate idea that I call the special condition, for want of a better name. And it is going to turn it into a sharper tool. So here's my version of the fixed point theorem. We have the same nature as before, as partial order with directed joins of these elements, inflationary monotone function, ender function, that satisfies this special condition, which derives from the more intuitive things that I mentioned before. And the result of that is we have a top element, it's the unique fixed point, and it obeys this induction principle, which was already in Zermelo's proof in 1908. That if we have some property that holds to the least element, is preserved by the successor and preserved by joins, then it holds of the top element, the unique fixed point. Okay. So we have this algebraic property. Let's apply it to some examples, and this is what I'd like to encourage everybody in the audience and all of your colleagues doing other mathematical subjects to try to do in your application, in your various forms of recursion that many people do. What are the well-founded elements of this structure? So all we have is a poset with directed joins and a successor operation of the least element, right? And in that situation, we have this notion of well-founded element. Simple piece of algebra, right? So you know that in category theory, you take the simple ideas. We have very few of them in category theory. They're very powerful tools. And when you apply those ideas in any new mathematical discipline, we find that it tells you exactly what research you have to do. This is our experience in category theory. This is a simple example of it. Characterise the well-founded elements of your structure. So here it is, going back to my leading example of the von Neumann's recursion theorem. So we just start with the power set of the set we're on. And we have a binary relation on it, and we can take successors of subsets. So we start off with the empty set, we have this successor operation on it, take all the things, all of whose predecessors are lying in this subset, and build up subsets like that. That's the successor operation. And then if you work out what it is to be a well-founded element of this structure, it is exactly an initial segment for which the restriction of the order is a well-founded relation. And then by Paterno's theorem, this has a greatest well-founded initial segment. Probably a fact that was known to Mechamanov in 1917. It's also in Paterno induction, and don't worry, that was on the previous slide, but I'm going to use it. So that's building up initial segments. So we find the greatest well-founded initial segment. So what about attempts? So once again, the attempts form a DCPO with the least elements of the successor operation. So you say, well, okay, how do we characterize the well-founded attempts? Well, that turns out to be a bit more complicated, but there's another way of doing it. We apply some algebraic, this is an algebraic idea, so we can apply some basic algebraic methods. So the successors, so the attempts and the initial segments are related by the support function, and the support function commutes, of course, with the successor operations. And so the way you find well-founded attempts is by using this idea. So, but as I say, algebraic. So we can said this, right? What can we use from that? The successor operation. Okay, the successor operation in the textbook version of this theorem lifts an attempt from a subset from an initial segment to its successor initial segment. But we can say more than that. It's actually a bijection. It actually restricts, and we have a bijection between the two. So that means to say that it preserves this property of the initial segment, that it has a unique attempt with that support. So successor preserves that property, and it's true of the empty set, and it's preserved by direct joints, right? So piece of algebra. So phi also holds of the unique fixed point, right? So this is practically right induction, and Martin Escalado was the first person to use it constructively, but it seems a no-no proof. So this my verbal commentary doesn't quite align with the slides. So what we've done is we've taken von Neumann's original proof, and we've completely dismantled it. There is almost nothing left of the original version of the proof. I've transferred everything to this elaboration of Paterno's theorem. So that means to say that we can apply it to much more complicated subjects. So in particular, in what I was originally studying, namely well-founded co-algebras, so we can start by taking sub-objects of the carrier, and we can ask and we can define the successor operation on those, and characterize the well-founded elements, and these are exactly the sub-co-algebras And the well-founded elements are the well-founded co-algebras in the sense that I wrote them sometime 30 years ago. So this could be applied to more complicated theories. So what I have in mind is that so the point is that well-founded co-algebras give you partial models of a free algebra that may not exist. So the original example is that there is no free algebra for the covariant power set functor. So the partial models of that are sets in the sense of set theory. And this is the idea that I'm trying to generalise. So I've got that for co-algebras, but there are more complicated situations where the theory is not just described by a functor, it's described by more complicated things. So I would hope that these methods would apply to that. So I'm going to give you some more examples of this. And the annoying thing is we have to move into well-powered categories, well-powered and co-powered categories, and of course the set theories come and say, oh, you need our set theory to do this. Well, that's rubbish, because well-powered categories have been defined using finite category theory, though frankly I'd like to have a better textual account than exists at the moment. We need the cancellation properties of monos and epis in order to turn a category into a pre-order, and of course the filtered co-limits give you the directed joints in the category. Right, so that's bookwork. Right, so here is a famous, allegedly difficult problem in category theory, namely finding quotients of algebras. So I'm just going to describe quotients of algebras for functors, but what I'm saying is very easily adapted to algebras for monads, and probably other kinds of algebras as well. So we want to find so here we have a pair of parallel homomorphisms between algebras of functor T, and we can construct the co-equalizer of the carriers. How do we construct the co-equalizer of the algebras? Well, we do some iteration by this diagram here. So what I'm going to do is to consider the disappear of epis out of X that have equal composites with F and G. And then, so these will factor through the co-equalizer of the carrier. So we copy the bit from copy this triangle up to here, right? And then form the push out. This is our successor. This is an epi so long as we assume that, what happened there? This is an epi so long as we assume that T preserves epis, and various other words like that. Anyway, that's the basic construction. So if the bottom map of that diagram is an isomorphism, then we get the map from the structure map from T, Y to Y, which is what we wanted. So that is to say, the co-equalizer of algebras is a fixed point for the successor function, and then so long as we can factorize epis and regular monos, you can check that this gives you the whole of the universal property that you want. Okay, so there's no ordinals there. We're simply using this version of Baccarat's fixed point theorem. And that repeats what I've just said. Okay, so going back to some of the things that I was interested in doing. So this looks like it's going to be the most powerful application of this. So recall that a relation is said to be extensional if when two elements have the same predecessors, then they're equal, right? So when you're a first year undergraduate, you think this is completely innocent. And it's absolutely not. So there's a famous theorem of Andrew Mostovsky using replacement and recursion that says that any extension or well-founded relation is isomorphic to a set. Well, I don't care about the ontology of sets, but more interesting from that, you can say, just starting with a well-founded relation, we can force it to be extensional by a construction of this kind. Well, of course, we don't need replacement, and we don't even need, well, we do need recursion. We can get a quotient by means of an equivalence relation, except the equivalence relation makes use of bisimulation, which is a word that we have heard before this morning. I don't know what quick connections are, but worth investigating. The equivalence relation is defined by co-recursion, so that's what I did in the 90s. I'm going to show you a piece of category theory that does this. So this is possibly one that's complicated diagram. So beta going from B to TB is a co-algebra, and the co-algebra is said to be extensional if the structure is mono. Well, it's not a mono to start with, so we can factorise it. So we factorise B as E followed by I up there, and these don't need to be homomorphisms, straight. Apply the function to this, and you find that everything around here is homomorphism for the co-algebras. And then, okay, so once again, we work in the co-slice of epis out of B, and of course we need to be sure that they form a set, in quotes, right? Perfectly possible to do that with fiber category theory. Right, actually, there's a mistake there which is corrected in the paper. The existence, the condition that you need to get to the top element of the unique fixed point in Atterai's theorem falls out very easily from this, then we can show that it has the universal property, so we compare it with an extensional co-algebra, and then the homomorphism here lifts to all these, lifts to the successor, and of course to fill the coordinates. Okay, so that idea is first applied to, how am I doing for time? Okay, so we're nearly there. So here now we're going to do some category theory. Right, so none of this depends on any particular category. Right, so my category can move from a topos to category of posets or to some other category. My monos and epis can be replaced by a factorization system, we may either set things up so that factorized theorem works and this thing converges, or it doesn't. Well, okay, so the case where it converges, working in posets instead of sets, we can recover not only sort of the Mostovsky theorem, but also the ordinal quotient of ordinal rank of a well-founded relation. Unfortunately, I can't possibly give a half-hour talk on the application, on the reformulation of ordinals in terms of co-algebras, because there are too many facts and fallacies to check there. But we will see in due course. Or we can consider the situation where it doesn't converge using Pateroid's theorem. So we have the idea now, this is the last slide, last one slide. This is, so we can think, we have this process, and you can encode the transfinite iteration of any functor in this categorical structure. So what I'm proposing here is to get rid of, I have no idea how what the estimate of replacement, the formulation of how you're supposed to use that. What I do know is that other mathematicians use transfer identity direction of functors. I can translate that into my generalisation of the Boskowski's theorem, and hence into a reflection of subcategories. Right? So what I'm proposing on my last slide, in memorial to Bill Lorvier, he taught us to use adjoints. He said everything is adjoints. So here is a general question for you. What functors may consistently, I'm not asking what functors have adjoints, what functors can be consistently assumed to have adjoints? This is my proposal. I will develop it in the future for a replacement for replacement, and the solution set condition doesn't answer that question. Okay, so
Thank you.
There is one question here.
So can you say something about the problems like generalizing to the setting of initial algebras, and like a lot of theorems about these least fixed points and these constructions somehow translate into construction of initial algebras with respect to some kind of end effectors. So, and you mentioned that there's a lot of problems. Can you say something about?
Okay, so the proposal is on the example of set theory, right? So that the covariant power set functor, not monad, functor has no initial algebra because it has no fixed points. But we have approximations to that in the form of set theory. So any transitive set, any fragment of set theory gives you an approximate to that. The union, the illegitimate union of those gives you the initial algebra. So if the initial algebra exists, then that's still true, except that in that case, the union, the colimit does exist.
There are two more questions, Paul, and they require quick answers. Paul?
No, my question doesn't have a quick answer. I'll ask Paul afterwards. Thank you.
Okay.
Walter?
At the end of the 70s, around 1980, I had a proof, a recorded proof of Birkhoff's subdirect representation theory of universal algebra. And at a later point, I discussed the proof with Bill Lorvier. And there was a little piece that needed ordinal induction. Bill's eyes were getting very big, and he just stared at me and said, ordinals, I don't know what they are. I think you have a partial answer to it. I didn't have.
Well, a lot of these problems, these things that allegedly require ordinals, Kuratowski said, no, you don't need that, you can do it with closure conditions. So I urge people, if you read any French, read Kuratowski's paper. I intend to give an English translation of it, right? Because the mathematical community should damn well have read that paper. As to, if I don't know the theory you're talking about, maybe you can tell me afterwards. The ones that can't be done in terms of closure conditions, well, maybe they require replacement, right? Could be an example of the construction that I have in mind. So.
Thank you very much, Paul.